Section 9.1, telling my muscles how to move. So how do we do this? How does this happen? So the learning objectives are to describe how neurons generate and propagate action potentials, and then how do we go from chemical information to electrical information back to chemical information. And so neurons are using these three components in order to communicate long distances, and they're doing this very rapidly. So how does all of this happen? Well, the first thing we need to dig into is to understand that there are differences in ion concentrations inside of the cell versus outside of the cell. And the cell is going to use these differences in these concentration gradients in order to do work, okay, in order to do something. And so if you look at the ion concentrations inside of a cell, you see that there's 155 millimolar concentration of potassium, and outside the cell there's 4 millimolar of potassium. So there's a big intracellular concentration of potassium and a small and extracellular concentration of potassium. If you look at sodium, it's pretty much reversed. So you have a very low concentration inside the cell and a very high concentration outside the cell relative to the inside. Calcium is very low inside and much higher on the outside compared to the inside. And then chlorine, the negative charge chlorine, is low on the inside and high on the outside. And so all of these differences in the concentration gradient, if you watched the previous two videos, you learn then that these differences gave rise to a charge across the cell membrane. So there's our cell, and inside the cell we have very, very low, so I'm going to make sodium small. We have really low sodium ion concentration inside, and the size of my drawing is showing you the concentration difference. And so we have very high sodium concentration on the outside, and we have very big concentration of potassium on the inside, and we have very little potassium concentration on the outside. So if we look at the differences in these concentrations, you might think, because chlorine is negatively charged and it's outside the cell and there's a lot more of it than inside the cell, you might think the outside has a high negative charge. But when you add up all the concentration differences here, what you find is that is not true. So if we draw this cell, and now we put in the numbers, what you're going to find inside the cell is you have a resting membrane potential. So inside of the cell, voltage of about -70, let's just say, millivolts. There's a voltage difference between the inside of the cell if we were to measure this with a voltmeter. Okay, what we'll find is that in reference, if the cell inside the cell is reference, so this is inside, then the needle is going to be pointing to the -70, not to the positive. It'll be negative compared to the outside. So this is inside, this is outside. And so this is a cell that isn't really doing anything, let's just say. It's just what we call resting potential. And resting potential is a very poor choice. It's the resting state or the resting electrical potential. It gives you the idea that the cell is resting. And so if this were a nerve cell, we're saying it's not actively electrically firing an action potential down the axon. But it isn't resting at all, because what we're going to learn is to maintain this negative inside compared to the positive outside. To maintain this, it's going to take a lot of ATP, which is going to be the energy source to drive then this concentration gradient or electrical gradient. It's going to be the energy source used to create a resting potential.